We welcome you at the Technical Forum at the Group Exhibit Hydrogen and Fuel Cells 2013. Please have a seat, have a free drink. You are really invited to listen to the next presentation and ask some questions at the end. Come and enjoy here with us the next presentation about hydrogen storage without the high pressure. Cella Energy from the research scientist Dr. Lyndsey. Here we go.
Good morning, ladies and gentlemen. Thank you for the introduction, Kirsten. As she said, I'm a research scientist for Cella Energy, and today I'd like to talk to you about the company as a whole, the fundamental research that we were conducting a couple of years ago, and the products that we're now bringing to market at the moment. Cella Energy is currently fundamentally an IP company. We're research scientists mainly, and we have been working on trying to use novel approaches to hydrogen storage to try and deal with some of the problems that is occurring using hydrogen, especially with fuel cells. We're trying to develop safe, low-cost hydrogen storage materials for power systems, primarily at the moment for transportation, but also for longer life batteries. Another subset of our company is radiation shielding, and I'd be happy to talk to you about either of those after this. But today I'm going to focus on transportation fuels as the main application for our long-term goals. The company has just turned 2 years old. It was originally 3 researchers at the Rutherford Appleton Laboratory in the UK, in Didcot, near Oxford. And the project was so successful it enabled a spin-out from the Rutherford Appleton Laboratory, which is where we're still located. Because of the radiation shielding work that was being conducted as well, we then had a second site that we've set up in Florida, in the States, for on the NASA site to enable that entry to market over there. We are focusing on a range of applications, as I mentioned, with diesel emission, zero emission, longer lasting batteries and radiation shielding. And we've got links to university research still to continue with the fundamental research, both there and within our labs at Rutherford. Our management team consists of the original inventor of the storage material, Professor Stephen Bennington, and our spin-out was facilitated by our CEO, who has a lot of experience working with small startup companies, and he's actually here at the fair if you would like to talk to him on our stand. Also at the fair this week is our Chief Operating Officer, Kevin Brundish, who brings an engineering background with him to the company. So we have a range of expertise. And then on our board of directors, we have links to fuel, transportation, aerospace, as well as the chemical industry, which enables us in many different ways. So why are we doing it? The demand for clean energy, well, for energy, is rising ever faster. The population is growing, but the demand for energy is growing at an even faster rate. But we're all trying to commit to lower emissions, and this is going to cause a problem. So everyone is trying to search for clean energy, and as this exhibit is testament to, hydrogen looks like a highly viable clean energy carrier. But there are, as I say, there's some issues with it and for its adoption. So we were trying to find ways to overcome these issues, and that's where the basis of the fundamental research came from. In the States, the Department of Energy has come up with a range of targets to help evaluate hydrogen storage materials to see if they would ever be potentially suitable or ever get to market. If you're not aware of these, they include that they want the storage materials to have an energy density similar to petrol to make the the applications run the same. They want you to have it to run close to room temperature and ambient pressures, again, so that the operating parameters are similar. Want to release and absorb hydrogen quickly, as well as they want it to be cheap, which is a great set of targets, but we also sat down and came up with some of our own, because we felt that wouldn't necessarily be enough to help us evaluate products that we feel would get to market. So we also thought that safety was of paramount importance. Consumers aren't going to want to use something that they perceive as being unsafe. Must be cheap. At this point, I don't think anyone can really afford to pay a high premium for green, clean energy. Must require minimal change to infrastructure. The reason we included this is the adoption within a country of a new fuel is going to have a hurdle to get over if there has to be large government investment in the infrastructure, and we felt we could probably come up with a better solution to that. And the performance must be adequate or similar. Adequate doesn't seem like a good enough word to me. I'd say the performance must be similar. So, considering the range of hydrogen storage materials available, MOFs, metal hydrides, these sorts of things, we actually looked at the chemical hydrides available, and after researching which ones look good, especially based on the DOE targets, ammonia borane seemed like an obvious choice. It has a very high hydrogen density, which are accessible at relatively sensible temperatures. This is because of the chemistry of the adduct that it's made from. So it's a Lewis acid adduct. And because of this very strong nitrogen to boron bond, if you heat the molecule, the hydrogens come off rather than it disassociating into ammonia and borane. It's this property that first showed that it could be used as a hydrogen storage material. So at relatively low temperatures, around 100 degrees C, the first equivalent of hydrogen comes off in this first polymerization reaction that you can see here. Then you heat the molecule a little bit more, another equivalent of hydrogen comes off. It's a very simple process. The only difficulty is the third equivalent of hydrogen, you have to go above 1,000 degrees C. And for the types of applications that we would be interested in, the temperature range is too high. So we're only considering the first two equivalents of hydrogen. It's a chemical that's easy to work with. It dissolves in many standard solvents, so processing in a lab is straightforward. The powder itself is a white waxy solid that melts at about 100 degrees, and it actually melts during this first polymerization step. The only trouble is well, not the only trouble, one of the major drawbacks is because it melts at this point and then it releases hydrogen, the material foams and it's very, very messy. And I don't know if any of you have ever worked with it, but it makes a gunky polymerized mess, which is a major drawback for some of the applications. So we were trying to come up with a way to improve the properties and make it safer to handle, nicer to handle. The other trouble is, whilst you can get these two equivalent of hydrogens out at sensible temperatures, they're still too high for a fuel cell. Fuel cells would rather run below 100 degrees C. So we were trying to modify the reactions that were occurring to see if we could bring down that hydrogen release temperature. We also wanted to try and improve the kinetics of the reaction because, again, the hydrogen comes out, but it comes out at quite a slow rate. So you need maybe minutes to hours to get out the hydrogen to power the fuel cell, which in a lot of applications wouldn't be suitable. What we came up with was making a composite material. So we blend it with polymers, and the action of blending it, and we now use a range of processes to do that, to make the composite. It improves the kinetics by an order of magnitude. It brings down the hydrogen release temperature, and it makes it safer to handle. It protects the ammonia borane from water, and it imparts mechanical properties that mean we could start considering other methods to use it. This is the material as it's processed. This is a SEM image, and then this is the same material that you can see here pressed into pellets. These pellets are about 2 centimetres in diameter. The other great thing that it did by blending ammonia borane with polymers is it stopped the foaming from happening. And by foaming, I mean bubbling all over the place. So on the left, you have ammonia borane pressed into a pellet, and then it went through a heating cycle. And this is where the hydrogen has been released, and the pellet has disintegrated and made a mess in the test tube in the lab. Our pellets, when you blended them with a polymer, made a composite, and you put it through exactly the same heating regime, the pellet remains intact. There is a very slight volume change, but we've worked very hard to process that out. So it now releases the same 2 equivalents of hydrogen at a lower temperature, faster, and it has structural integrity. This actually shows evidence that we've altered the chemistry that's happening. Ammonia borane, when you heat it on its own, you have this type of hydrogen release profile. This is indicative of a nucleation and then growth type change in your reaction. Whereas our material, there's no induction phase, so the chemistry that's happening has actually changed. This also shows that the material, the tissue-like paper that you saw on the other slide, is this curve here, and pressing it into pellets didn't affect that. Once we got a product that worked, we tried to push up the hydrogen content. We've investigated other ways to process it to bring down the cost of the material as a fuel. And we've started to investigate different ways we could use these pellets. And I want to talk to you about one of the specific applications today. So just to recap, we process ammonia borane with a plastic to make a composite. It changes the hydrogen release properties, it makes it safer, it makes it more easy to handle, and there are no high pressures or high temperatures involved in the hydrogen release from this material. Because we can press this into pellets, you can make the equivalent of a fluidized bed out of it. So you can flow pellets like a fluid. And because of that, we came up with the idea of having it as a fuel that could be pumped into a vehicle the same way you would pump diesel or petrol now. You could then heat the pellets as and when you needed it during the vehicle being in use. And then that hydrogen that's released from the material would then fuel a fuel cell and you could run your car. So the idea of this schematic is just to show you that you would have beads, as I showed you, or pellets, as I showed you, that could then be discharged from a storage tank in a vehicle into a hot cell. You'd heat the hot cell, you'd release hydrogen into a buffer volume so that you could have a continual use of your fuel cell and it could cope with the demands of different driving profiles. It would power your fuel cell, and then the spent pellets that have had its hydrogen released from it would go into a separate portion of the storage tank, and then you would pump these out when you went back to a refueling station when you pumped in fresh pellets. We've got a much better version of this on our display over on our stand if you'd like to come and have a look. This is our longer term aim. We have other applications that we're using in the shorter term, but this is our idea of how to get to a zero emission vehicle. We did some calculations to see if our system performance would be adequate, comparable, just see how they would stand up against competitive fuels, and we were pleased to find out that our Cella system is competitive, but not only that, it hits the US DOE targets already, and that's before we continue our research to push up the hydrogen content and improve on the product. We also conducted a well-to-wheel analysis to understand the carbon footprint that you would generate from our material, and we were again pleased to find out that in the driving range that the DOE wants everyone to hit, which is the one fill of the tank to give you 300 miles, our material is competitive, and it's similar to other future fuels, as in the carbon footprint comes from the processing of the fuel, not when you burn the fuel in the car. If you then could run the production side of things with cleaner energy, the carbon footprint is greatly improved. Because we are pelletizing our material and flowing it like a fluid, it means we can have any geometry we want or the customer wants for the fuel tank. That means that we can fit into the irregularly shaped tanks that you already have. You don't have to have one block in the back of your car with our fuel in it. It can fit wherever you like. It could fit into cars as they are now, or it could fit into the skateboard type idea that people are hoping to get to, with fuel cells and the fuel on the base of a car, and then you can build your car however you want it over the top of that. So just to recap, we have a familiar customer experience, because you could go to a refueling station and pump in fresh pellets, pump out old pellets. Hopefully, well, we anticipate within the same sort of time frame that it would take you to fill your car up with petrol as it is now. You don't have to leave your car charging for however long, and it would be not that dissimilar to the infrastructure that is already in place. Because there's no high pressure involved, you wouldn't need a specialist to fuel your car for you. You would, again, be able to drive up, pump in the pellets yourself, and then drive away again. It's this type of thing that we believe will make the product viable and would be adopted by the market. That is the zero emission application that is our longer term aim. We also are looking at diesel abatement, where you could bleed in, let's say, 5-10% of hydrogen into your diesel internal combustion engine and provide a cleaner burn in your diesel and bring down the emissions of diesel trucks, diesel cars, which is becoming more important considering the low emission zones that are implemented across Europe now. We're also looking at longer duration batteries, either extending the life of them or replacing them. And at the moment, our Generation 1 material provides 3 times the energy density compared to a lithium-ion battery, and we're hoping to get it up to 6 times. On the complete opposite side of that, we have the space radiation shielding, which is to do with the hydrogen content of a material absorbing and neutralizing the radiation from space, which I won't go into now because it's a whole other presentation. Just some details about the other transport fuels if we have time. So just to recap then, I won't go into it in detail. The other option is diesel abatement, where you could buy a certain quantity of the pellet, release hydrogen into your tank, get a cleaner burn, reduce your emissions. The longer duration batteries, we're currently looking at military applications for soldier power, because they have to carry around large packs and lots of spare batteries with them, whereas for the same weight we could provide them with, as I say, 3 times the amount of energy that they currently have, which means they could carry other things. And we're also looking at UAVs at the moment, which we have an example of on our stand if you'd like to come and have a look, and we can talk it through there. I won't go into the space radiation shielding, but I will show you the value chain for our company at the moment, because we thought we would just sit here as a company and have IP and the material processing and manufacture, but it turns out that we're actually ending up with IP and collaborations downstream and upstream from us to make this, to get this to market. And it's this sort of end of the chain that we're looking for collaborations and for new partners. We've already got the material ready. We know how to make it. We're constantly improving on it. And we're now in the prototype stage this year. And looking to do initial testing next year. We're talking about benchtop demonstrators and early prototypes. And then in the slightly longer term, we're at the point of doing field trials to hopefully come with good data and show that this is viable. And that is it for today.
So thank you, Lyndsey, for this interesting presentation.
Thank you.
So, of course, I just want to say my sentence. Okay, now you have the opportunity to ask some questions and to make some remarks or comments. And yes, I will come to you soon.
Thank you. I have 3 questions.
Sure.
The first one was you wanted for transport applications, but you said one of your requirements was to have it at room temperature or ambient. For normal transport, you need temperatures from -40 to +40.
Mm-hmm.
Is that viable?
That is. We've already conducted storage tests going up to 60 degrees to check that the hydrogen won't be released, and I'm pleased to say that it's stable. The kinetics are so slow that you would consider it stable.
Okay, thank you. The second question, you said that your 2 reactions at 110 and 180 degrees.
That's for ammonia borane.
Borane. The third one you said was at 1,000 degrees. Wouldn't that be suitable for internal combustion?
I'm not sure if it's the efficiency that stops it working for that. I'm not entirely sure about that one. I mean, what temperature does an internal combustion engine go up to? Because some people report the third equivalent of ammonia borane coming out above 1,000, some 1,200, and it may be that there's a bit of discrepancy and you don't quite get to it.
In high temperature combustion, you do get above 1,200 degrees.
Okay.
So that would be a viable alternative from my point of view.
Thank you. I'll look into that.
Thank you. And the third one is, with so much ammonium, what about the NOx emissions or the emissions during combustion?
We're looking into coating the pellets to hold in any impurities so that we can clean up the hydrogen supply and release whatever level of hydrogen purity is required by a fuel cell. And then we would deal with those impurities at the recycling stage. When you take it away from the customer, you take the beads to be regenerated.
It's your turn.
Okay, thank you.
Hi.
Part of my question has already been answered, but I have a doubt about the hydrogen evolution, the kinetics of hydrogen evolution. When you heat up your tank containing the pellets, let's say at 85 degrees, does all the hydrogen comes off all together? Because, I mean, in this case, you would need a hydrogen storage system in any case.
We're trying to tune it so that we can tweak the hydrogen release depending on the application. For the transport fuel at the moment, we're trying to hit that from each individual pellet you would get the hydrogen released within, let's say, a 3-minute window. Yeah. Because if we can tailor the hydrogen release specifically, then we can design the hydrogen buffer volume to be the minimum that it needs to be safe. So that, let's say you turn your car off and it's set off the last pellet, you then have a buffer volume to deal with. So we're trying to look at the size of the pellets to see what is the best way to have that geometry, and also to look at the hydrogen content and the material we're blending it with to improve or to fully tailor that hydrogen release.
So, I mean, this means that for real portable applications, like for a portable power generator, it takes some time to tune the technology.
Yes.
Yeah. Thank you.
It's a lot more demanding for the portable power.
Hi. My question is about the. You've mentioned the energy density of this material. Can you say something about the actual gravimetrical density?
The density at the moment stands at 3,000 kilowatt hours per kilogram, or 2,400 kilowatts. Sorry, kilowatts, not kilowatt hours. Kilowatts per litre. If that helps.
Could you repeat that?
So it's 3,000 for gravimetric, and 2,400 for
per litre. Okay, thank you.
Dr. Borane, thanks for a very interesting presentation. Question, what do you do with your spent pellets?
Regenerate them. So recycle, strip out the polymer, regenerate the ammonia, borane, put it all back together again.
Okay,
reuse.
So that logical question, where do you take your hydrogen from?
Good question.
Yeah, because
So-
this will affect your economics. I mean, when you are
Yes.
comparing, compressed hydrogen with your pellets, you probably didn't take this into account, because that would affect the energy mix that goes into the hydrogen production.
I didn't do that analysis, but
No, I know, I'm just pointing this
I was
out.
just going to say we could check that. I can check
Right.
whether or not that was included. I don't know if it was or not at this stage.
Okay, maybe you can talk at the booth
Sure.
from you, E69. Yeah. Okay. Thank you again, Lyndsey, for being here for this very, very interesting
Thank you.
presentation. Just please staying here. We will continue our presentations here with from NGK Insulators, dealing with the features and latest applications of NAS battery system. Thanks a lot.